The space race of the 1960s sparked a whole wave of wild ideas, getting through the Van Allen belts, landing humans on the moon, and somehow bringing them safely back home. But after Apollo funding dropped, public interest faded, and humanity's push into deep space slowly lost momentum. But what if that never happened? What if the world kept pushing forward aggressively into space, building massive rockets, permanent moon bases, and eventually colonies on Mars and beyond? The crazy part is that NASA and aerospace engineers actually had plans for a future like that. One of those concepts was a rocket so enormous and powerful it could have accelerated the construction of off-world colonies by years. Even better than SpaceX Starship. This is the story of Sea Dragon. Back in 1962, many people believed the future of spaceflight would explode in the following decades. By the 1970s, 80s, and beyond, it was expected that thousands of people would be living and working in space, on the moon, and even on Mars. To make that possible, rockets with massive lifting capability would be needed to dramatically lower the cost of transporting materials into orbit. Out of that vision came one of the most ambitious rocket concepts ever proposed: Sea Dragon. The rocket was designed by Robert Truax, a U.S. Navy captain and rocket engineer who helped pioneer early American rocketry. During his career, he worked on major missile programs like Thor and Polaris, and his team even debriefed German rocket engineers after World War II, including Wernher von Braun, who would later go on to design the Saturn V. But Truax had a very different philosophy when it came to rockets. He believed the biggest reason rockets were so expensive was not their size, but their complexity. So instead of building rockets that were smaller, lighter, and increasingly complicated, he imagined the exact opposite. Sea Dragon would be absolutely gigantic, but also rugged, simple, and relatively cheap to build. The idea sounded almost crazy, but at the same time, surprisingly practical. At liftoff, Sea Dragon would have weighed around 40 million pounds, or about 18 million kilograms, making it far larger than any rocket ever built. The rocket was designed to stand roughly 500 feet tall and 75 feet wide, completely dwarfing even modern giants like SpaceX's Starship. In a way, you could almost imagine it as an extremely wide version of Starship, and with that enormous size came an equally insane payload capacity. The reusable version of Sea Dragon was expected to carry around 500 metric tons into low Earth orbit, roughly 5 times more than what SpaceX Starship is currently aiming for. An expendable version could have pushed that number even higher. However, building a rocket this massive created some huge challenges. The first problem was simply transportation. Moving individual parts would already be difficult, let alone transporting the fully assembled rocket. Its sheer power was another major issue. Sea Dragon's engines would have produced so much thrust that they could have destroyed any existing launch pad. Then there was the exhaust plume itself, which could have stretched nearly 1 mile, or around 1.6 kilometers long. Because of all these problems, Sea Dragon was designed to launch from the ocean, which is where its name came from. And incredibly, it would not launch from a floating platform, but from partially beneath the water itself. If you're wondering why the water wouldn't put out the engines, it's because the rocket carried its own liquid oxygen supply. Just like rockets that operate in the vacuum of space, where there's no air, Sea Dragon didn't need oxygen from the atmosphere to burn its fuel. And once the engines ignited, the enormous thrust would simply blast the water away from the engine bell. Sea Dragon would be built using shipbuilding techniques. Major sections of the vehicle would be constructed in shipyards, floated into the water, and then towed by tugboats to an offshore assembly area near Cape Canaveral. The first stage, the second stage, and the payload section would all be connected together horizontally while floating in water. One of the rocket's most unusual features was its sea-based launch system. Sea Dragon would float freely in the ocean before launch. A large ballast system attached near the bottom of the first stage helped stabilize the rocket during towing and preparation. Once the rocket was ready for launch, the ballast would help rotate the vehicle upright in the water before being released shortly after liftoff and later recovered. Now let's get a bit more detail about the design of this massive rocket. Sea Dragon's entire design philosophy focused on simplicity, durability, and low cost. Unlike most modern rockets that rely on highly complicated turbopumps and many small engines, Sea Dragon used only one enormous engine on each stage. Both stages used pressure-fed propulsion systems, meaning the propellants were pushed into the engines directly by tank pressure instead of high-speed pumps. This approach greatly simplified the engines and reduced the number of moving parts, although it required much stronger and heavier tanks. Because of this, the tanks themselves became a major structural part of the rocket. The vehicle's giant propellant tanks were designed like massive pressure vessels that stayed pressurized during transport, fueling, launch, and flight in order to maintain structural strength. The first stage used RP-1 kerosene fuel and liquid oxygen, while the second stage used liquid hydrogen and liquid oxygen for better efficiency in space. The first stage engine could swivel or gimbal to steer the rocket during ascent. The second stage relied on smaller auxiliary engines for steering and roll control during orbital insertion. The upper stage also featured a huge expandable nozzle. Part of the nozzle was cooled by flowing hydrogen fuel, while the outer section radiated heat into space. The nozzle would remain compact during launch and then expand after staging to improve efficiency in vacuum conditions. Sea Dragon was also designed with reusability in mind, especially for the first stage. After separation, the booster would deploy a massive inflatable drag skirt, sometimes described as a drag bag or conical flare. This system would slow and stabilize the stage during re-entry so it could survive a controlled splashdown in the ocean. Engineers believed the booster could then be recovered and reused with relatively minor refurbishment. Reliability was another major focus of the design. Since the rocket was so large, many systems could operate under lower stress compared to smaller launch vehicles. Engineers intentionally avoided overly complex designs and instead favored conservative structures, simple plumbing systems, and proven technologies. Even the valves and feed systems were designed to separate functions whenever possible in order to reduce failure points. Sea-based operations also offered major advantages. Launching far offshore reduced risks from noise explosions or falling debris, while the ocean itself acted as a natural transport and recovery system for the giant rocket stages. Guidance and control would come from an Apollo-style command module mounted with the payload. This module contained the inertial guidance system, communications equipment, and flight controls. After the mission, it could separate from the vehicle, re-enter Earth's atmosphere, and safely splash down for recovery. With all of that power in mind, what would a Sea Dragon launch actually look like? What would its operational sequence be like from liftoff to touchdown? Sea Dragon's operational cycle was designed more like a naval operation than a traditional rocket launch. As I said earlier, construction would begin in shipyards where the massive stages were fabricated using techniques similar to those used for large ships and submarines. Once completed, the stages and payload sections would be floated into the ocean and towed separately to an offshore assembly lagoon near Cape Canaveral. In the lagoon, the rocket would be assembled horizontally while floating in calm water. Workers would connect the stages, install the payload and command module, and attach the large ballast unit near the bottom of the first stage. Smaller components and support equipment could be delivered separately by truck or aircraft. Fueling happened in multiple steps. The rocket would first be loaded with RP-1 fuel and liquid hydrogen before being towed to another location where liquid oxygen would be added by a specialized support barge. Since the rocket operated entirely at sea, its fueling and vent systems were specifically designed to function reliably while floating. After fueling, tugboats would tow the fully assembled vehicle around 40 miles offshore to the launch site. To prepare for launch, the ballast system would be flooded with water and dense drilling mud, pulling the bottom of the rocket downward and rotating the entire vehicle into a vertical position in the ocean. Before launch, the crew would board the command module using a small, elevator-like service vehicle running along rails mounted to the rocket's side. During the countdown, the small auxiliary steering engines would ignite first to stabilize the vehicle. Then, the enormous first stage engine would ignite underwater. As the rocket rose out of the ocean and began climbing, the heavy ballast system would detach and sink temporarily before later being recovered using inflatable flotation bags. The first stage would burn for about 81 seconds, accelerating the rocket to roughly 1.77 kilometers per second and carrying it to an altitude of around 38 kilometers. At staging, explosive separation charges would push the empty booster away from the second stage. The upper stage engine would then ignite, and its expandable nozzle would deploy to full size for efficient operation in space. The second stage would continue accelerating the payload toward orbit, while the auxiliary engines handled steering and stabilization. About 22 minutes after liftoff, Sea Dragon would reach its planned orbit, roughly 567 kilometers above Earth. Meanwhile, the empty first stage would coast upward to an altitude of over 100 kilometers before beginning its descent back into the atmosphere. During re-entry, the inflatable drag flare would deploy and dramatically slow the booster. Although the returning stage would experience significant deceleration forces, engineers believed the pressurized structure would survive the impact with the ocean. After splashdown, tugboats would recover the floating booster and tow it back for refurbishment and reuse. At the end of the mission, the command module would separate from the payload, re-enter Earth's atmosphere, and perform a standard ocean recovery, similar to the Apollo program. Although Sea Dragon was never built, mostly because of shifting budgets, extreme engineering risks, and the lack of an immediate need for a rocket capable of carrying 500 tons into orbit, it still remains one of the boldest launch vehicle concepts ever seriously studied. Its focus on simplicity, enormous payload capacity, ocean launches, and partial reusability was decades ahead of its time. And honestly, many of its ideas still feel surprisingly modern today. And interestingly, the concept never completely disappeared. In 2002, a low-cost sea-launched rocket called Aquarius was proposed. It had a very similar philosophy to Sea Dragon, although on a much smaller scale. The idea was to cheaply deliver supplies and consumables into low Earth orbit for places like the International Space Station, but the project was ultimately never selected. The U.S. Navy also researched sea-based rocket launches and found that launching from the ocean could actually be smoother and less stressful on the vehicle compared to a traditional land launch. In many ways, the ocean makes an excellent launch platform. It's essentially indestructible, requires very little infrastructure, and naturally helps absorb shock and noise. Even small ocean swells could be tolerated, while the dense water around the rocket would help guide it upward during the first moments of liftoff until it fully cleared the surface. So, could Sea Dragon, or something inspired by it, ever make a comeback someday? Let me know what you think down in the comments below. And by the way, more than 90% of viewers watching are not subscribed yet. So, if you enjoyed this video and want to explore more of the incredible world of spaceflight, don't forget to leave a like and subscribe to the channel. Thanks for watching.